Now we're going to set up the topology of our neural network itself. So that's what neural net here does. And as we said in the slides, you can define these fancy neural networks as just simple matrix multiplication and addition functions here, right? So we'll start off by saying tf.matmul, that's just a matrix multiplication of our input neurons, which is the raw 784 pixel values, with the 512 weights in our hidden layer of neurons there. So that matrix multiplication is multiplying each one of those input values by the weights in that hidden layer. We then say tf.add to add in the bias terms, which again are stored in the b variable that we just defined above. Okay. Next, we need to apply a sigmoid function to the output of that hidden layer. So that's basically the activation function on each hidden neuron. Okay, that's all that's happening there. Very simple. The output layer, we'll do it again. So we'll say do a matrix multiplication with our output weights and the hidden layer, and then we'll add in those output biases at the end as well. And we'll call softmax to actually normalize those output neurons to a final probability of each individual classification. So softmax, again, is just a mathematical trick for taking the outputs of these neural networks and converting those output neuron values to what we can interpret as a probability of each individual classification that those neurons represent being correct. Go ahead and execute that. And that's quick as well. Again, remember, all we're doing is defining our graph at this point. We're not actually training anything or running anything yet. But yeah, do take the time to noodle on that. We have basically constructed the topology of the neural network itself. The next thing we need to do is figure out how to actually train this neural network, right? So again, we're doing this the hard way, so we have to write this by hand. We'll start by defining our loss function, and it's called cross entropy. Basically, it's a way of doing gradient descent. It's applying a logarithmic scale, and that has the effect of penalizing incorrect classifications much more than ones that are close to the correct answer. That's a handy property for making training go quickly. So within this function, we're going to pass in two things. Ypred is the predicted values that are coming out of our neural network, and ytrue are the known true labels that are associated with each image. So we have to talk about one-hot encoding at this point. We talk about this when we talk about feature engineering in the course, but in order to compare that known value, that known label, which is a number from 0 to 9, to the output of this neural network, remember the output of the neural network is actually 10 different neurons, where each one represents the probability of a given classification. To actually compare that to the known correct value, we need to convert that known correct number to a similar format. So we're going to use one-hot encoding. It's best understood with an example. So let's say that we know that the answer for the known correct label for an image is 1. We would one-hot encode that as a 10-value array here, where each value represents the probability of that given classification. Since we know with 100% certainty that this image was a 1, we can say that for the classification 0, there's a 0% chance of that. For the classification 1, there's a 100% chance of that, 1.0. And for 2, it's going to be 0. For 3, it's 0, so on and so forth. So that is one-hot encoding. You're just creating a binary representation of a integer value, if you will. So the number 1 is represented as 0, 1, 0, 0, 0, 0, 0. Every one of those slots in the array there represents a different classification. In this case, we're going to use stochastic gradient descent. We've talked about that before. And we will use our learning rate hyperparameter, which again, we'll want to tune through experimentation later on to define that optimizer. We need to write a function to actually run that optimization. And again, with the lower level TensorFlow APIs, we kind of have to do this the hard way. We're going to use something called gradient tape to actually do this automatically. What that's doing, as you can see here, is actually calling our neural net function that defines the topology of our neural network. We're going to compute the loss function, our cross entropy function that we defined above as well. So this is tying it all together and actually allowing us to optimize this neural network within this one function here. So not terribly important to understand what's going on here at a low level. You can kind of understand here through the comments. We are updating our variables as we go through each step here. We compute the gradients, and then we update our weights and biases at each training step. So this code is what's computing new weights and biases through each training pass. Again, this is going to be a lot easier using the Keras higher level APIs. So right now we're just showing you this to give you an appreciation of what's going on under the hood. Let's go ahead and shift enter that one as well. All right, so now we have everything we need. We have the topology of our network defined. We have the variables defined for our weights and biases. We have a loss function defined, which is cross entropy. And we have an optimization function that ties it all together called run optimization. Let's go ahead and start training this thing. So that's what's going on here. Oh, wait, one more thing. We need an accuracy metric as well. So a loss function isn't enough. We also want to display the actual accuracy at each stage too. And all this accuracy metric does is say, let's compare the actual maximum argument from each output array that's going to correspond to our one hot encoded value, and compare that to the one hot encoded known value that we had for that label. So this is just a way of saying we're going to call reduce mean to actually compute the accuracy of each individual prediction and average that across the entire data set. So that's what our accuracy